Alrighty, folks, so today we are talking about section 10.1, which is where we set up our whole idea of hypothesis testing, which is one of the big things that we're intending to get out of this class, and what we're going to be spending this last week on. So when we are going about performing a hypothesis test, there are 4 steps. The first one is to state our hypotheses. So we always have 2 hypotheses, and they are called the null hypothesis and the alternate hypothesis. Once we've got those stated, once we've figured out what are the things that we are testing, then we should have enough information to determine the distribution in question and the level of significance. Once we've got all that set up and we're ready to go, then it's time to gather data. If we're in the real world, in this class, the data will usually be given to us in the form of a word problem. And so our part in this step is to calculate, well, for us we're usually going to be finding, but calculating the sample statistic. Well, never mind. We'll have to do plenty of calculating that. And then the last step is to draw a conclusion, right? So a hypothesis test will always result in a conclusion, and it's going to be just as important that we understand how to interpret that conclusion as it is that we know how to draw it. So to go at this in order, for 1, the null hypothesis is always denoted H naught, right? So H subscript 0. That subscript 0 is generally pronounced naught. This is always going to look like the parameter equal a value. Always, for our purposes. In some fields, it'll look slightly different. So if you get to someone teaching you about how this stuff works in your specific field, then don't counteract and tell them they're dumb and stupid because I said so, because I'm certainly not saying that. For our purposes, the null hypothesis will always have an equal to. Generally, there'll always be an equal to involved. There just might be something else to it. But for our purposes, the null hypothesis is always going to be an equal to statement, right? This is supposed to represent the status quo, what is currently believed, right? This sort of represents the default, right? So those are the types of ideas that you're looking for in word problems to tell you what the null hypothesis is going to be, is what is standard, what is usual, what has been shown in the past. What is the status quo? What is it? What have people thought it was, right? And our alternative hypothesis is similarly H with a subscript, but it's H subscript A, which is a little bit trickier to tell in handwriting than in typing. It's sometimes called H1, but it's more common HA. And this is always going to have the same parameter as H naught, and it's always going to have the same value as H naught. The only sort of choice you're making when you're coming up with an alternative hypothesis is it going to be less than, is it going to be greater than, or is it going to be not equal to? Right? So, oops, there we go, not equal to. Right, so I'm not saying that one alternative hypothesis includes all of those. I'm just saying that these are going to be set to the same thing that your null hypothesis is. Right, this is the thing that you wind up choosing whenever you come up with an alternative hypothesis. Right, and so this is the thing you are trying to support. It's also called your research hypothesis, right? So if you think that something is wrong with what's currently believed, if you think that the status quo is incorrect, then that's when you do hypothesis testing, and the alternative hypothesis represents what you think is true instead, right? Instead of the average being 5, maybe you think it's more than 5. Or maybe you think it's less than 5. Or maybe you don't know what it is relative to 5, but you're just pretty sure that at least it's not equal to 5. Right? So that's where we get our alternative, our null and alternative hypothesis for. 2, we have sort of a checklist. If the parameter in question is mu, then, as should be familiar at this point, considering we've done this twice now, if sigma is known, that means our distribution is normal, and our test statistic is the one it always is for a normal distribution. X bar minus mu over sigma divided by the square root of n. Right? If we have the parameter mu, but sigma is unknown, right, then same as it's been for the past 2 times we've dealt with something talking about mu with sigma unknown, the distribution is students t, and the test statistic is the test statistic that it always is for students t, which looks a lot like the one for mu with sigma known, except since we don't know sigma, we replace its part in the formula by s. All right. Now, we might also deal with a parameter of p. We're not going to in this class because we're going to run out of time. But you can do this with proportion, same way we did sample distributions with proportion, same way we did confidence intervals with proportion. And same as all of those, the distribution is normal, and the test statistic is the same as it's been for all of those. P hat minus P divided by the square root of P times 1 minus P all over N. Right, like I said, I just wanted to include this for completion. We're not actually going to be doing anything with that in this class. Right, so the other part of section 2 was level of significance. I'm going to put a pin in that for right now because there's some stuff that comes up in in step 4 that makes that more meaningful. Right, so this is technically also, to note, part 2 and 3, because this is the test statistic that you'll be calculating here in step 3. Like I mentioned, if you are doing this in your field, then you'll often be in charge of gathering the data. In this case, I technically be gathering it, but you'll be gathering it from a word problem. So it's not quite the same deal, but you are still going to need to calculate that sample statistic, and you'll be using one of these 2 formulas depending on whether you know sigma or you don't know sigma. Right? So in step 4, we're going to draw a conclusion, and it's always going to be one of two conclusions. Right? There are only two possible conclusions to a hypothesis test, and that is you can either reject the null hypothesis or you can fail to reject the null hypothesis. Right? So those are two possible conclusions, right? And I'm going to draw a box here to show all possible outcomes that happen there, right? So we can reject H naught, we can fail to reject H naught, and we won't know this because the reason we're doing statistics is we can't know this. But if we're considering all the possibilities in the world, there's two possibilities. Either H naught is true or H naught is not true. Right? So if we reject H naught and H naught is incorrect, then we did the right thing. Right? If our conclusion is we want to reject H naught and H naught was incorrect, we should reject it and we were correct in what we did. Right? Now, if H naught is true and we fail to reject it, we have also done the correct thing. Right? Because we don't want to reject a statement if it's true. Right? So these two boxes represent the two possible situations that we want to happen. Right? We want to have done the correct thing. We want to have correctly identified which hypothesis is correct. Right? So both of these two possibilities are errors. Right? If H naught was true but we rejected it, then we made a mistake. Right? Not like a mistake in that we did our math wrong, but a mistake in that we're doing things with probabilities, and so we don't have a guarantee of getting the right answer. Right? Same for if H naught is not true, but we fail to reject it, then we've also made a mistake. And these have names. This is a type 1 error, and this is a type 2 error. All right? And this is the part where I can bring back that level of significance in. Right? So the level of significance is always going to be denoted with an alpha, and that's the same alpha that we dealt with for hypothesis testing, i.e. this is the same one that's 1 minus C, right? So the opposite of the confidence level, right? But as it turns out, there's a reason why it has its own letter associated with it rather than always just being 1 minus C. And that's because alpha is also the probability of making a type 1 error. So when you see a problem saying, do this work with a level of significance of 0.05, that means we have a 5% chance of rejecting H naught even though it was true. Right? If you see an alpha of 0.1, that means you have a 10% chance of rejecting H naught even though H naught was true. Right? So when we choose this level of significance, we are in a sense deciding how okay we are with making a type 1 error. Right? And it just so happens that if you decrease the likelihood of a type 1 error, you increase the likelihood of a type 2 error. Right? So there's a complicated formula that we won't be worrying about. This one is beta. So if you see something talking about beta, it's probably in statistics stuff, it's probably talking about the probability of a type 2 error. But we're not going to be dealing too much with that. We're going to be focusing on this level of significance, which is the probability of making a type 1 error, and we want to make that as small as we can, generally, right? If there's not too much of a problem, right, if there's no consequence for rejecting H naught, then maybe we're a little bit more okay with making that particular error, even though we might reject H naught incorrectly, right? But that's just something to keep in mind. Most of the problems that you're working with, the level of significance will be given to you, so you won't have to make decisions like that. And one of the things when you learn to do this in your particular field is there are often some guidelines or some ways of thinking about it that help you decide that alpha. But it's the alpha is always going to be this probability of type 1 error. All right. So I think that's about it. So I have some word problems here. We're not going to actually do the hypothesis testing, right? All of them say things like determine or construct. Well, this one just says construct the hypotheses or test using confidence intervals in that case. And so that sort of thing. So we're going to ignore those part of the instructions and just talk about finding our hypotheses, and figuring out our test statistic, right? Because those are fairly standard all the way through. So let me, whoops, that's not helpful. Grab these guys, bring them down a little bit. Grab the first problem. Bring it up a little bit. Alrighty. So here we have a manufacturing making claims about how thick the gum it produces is, right? And then we have someone who is checking this claim, right? So right off the bat, we can see that this sentence is probably telling us about the null hypothesis because it is a status quo. It is the claim that is being tested, right? So it seems like our H naught is going to be that the average thickness is 7.5 1/100ths of an inch, right? And that means we can go ahead and set up our alternative hypothesis without going any further. That's going to be mu is something to 7.5, right? And we just need to pay attention as we read to figure out whether that's less than, greater than, or not equal to, right? So this sentence is just sort of setting it up. So it tells us, took a random sample and gives us n equals 10, right? So that's something that's nice to have right off the bat. The average thickness was 7.55. So that was the average thickness of the 10 pieces of gum. So that's going to be X bar. Right? So average means it's either going to be X bar or mu. And the fact that it's of the 10 pieces rather than of every single piece of gum ever is the one that tells us that it's X bar. And since this is the same sentence, this tells us that S equals 0.102. Right? We still haven't gotten that alternative hypothesis, but we have one more sentence left to go. Right? So it says, determine whether or not the average thickness of the gum produced is different from the manufacturer's claim. Right? So it doesn't say less than, it doesn't say more than, it doesn't give any sort of comparison words. It just wants to test whether it is at all in any way different from what the status quo is, what the manufacturer's claim is. Right? And then lastly, it tells us what alpha is. Right? So we've got our hypotheses set up here. Right? We the other thing we can do at this point is find our test statistic, right? We don't know the population standard deviation. The only standard deviation we were given was in the sentence that was describing sample data. So that means that we're going to be looking at t equals, right? And if we recall from the formula up there, it's x bar minus mu divided by s over the square root of n. So this is 7.55 minus 7.5 all over 0.102 over the square root of 10, which, when I plug into my calculator, I get 1.55. Now, the reason why we do this test statistic is that it's going to be essential in the drawing a conclusion step, right? That step number 4 was to draw a conclusion, which is either going to be reject or fail to reject H naught. Our conclusions never say anything about the alternative hypothesis. It's always reject or fail to reject H naught. And we're always going to use this test statistic to do it. But figuring out how to draw a conclusion is for later, right? But for now, I'm going to say, suppose we fail to reject, right? That's one of our two options. So without worrying about why we did that yet, right? If we were going to interpret that conclusion, right? The math is always going to lead to a conclusion of reject or fail to reject H naught. And when we interpret that, that means bringing it back to the word problem aspect, right? Failing to reject always means that we don't have enough evidence to say that the alternative hypothesis is true, right? So in this case, or we don't have enough evidence to say that the null hypothesis, rather, is not true. So we don't have enough evidence to say that this statement is not true, right? And that statement is talking about the average thicknesses of gum. So we don't have enough evidence to say that the average thickness of their spearmint gum is not 7.5. Right. So that would be our interpretation of this conclusion, right? Our conclusion is one of those two things. But we're going to get different interpretations based on the word problem that's built around us. Now just to push this a little further, let's say, suppose the average thickness of the gum is actually 7.52, right? So in this case, we failed to reject H naught, right? But it turns out that H naught wasn't true, right? So if we go back to our chart, we failed to reject H naught, but it turns out H naught was not true. So we committed a type 2 error. So then our conclusion was a type 2 error, right? Because we failed to reject H naught, but it turns out that we actually should have because H naught wasn't true, right? Alrighty, so let's get another problem set up here. Get ourselves some room. Hopefully that'll be enough. Right. Alrighty, so this first sentence, a consumer group is worried about the mean fat content in certain grade of steak burgers. So right off the bat, that tells us that we're probably dealing with averages, right? So our H naught is going to be mu equals, our HA is going to be mu something. We don't know the middle part yet. Right? So they took a random sample. They're telling us about the sample data first. And straight off, they tell us how big the sample is. And then it tells us about the sample's average fat content. Right? So it's the sample's average. So that's going to be X bar is 21. Now here we have something tricky, right? Because again, we have a manufacturer's claim about something. But that manufacturer's claim is not an equal to sign, right? So this is one of the cases where in certain fields we might actually include a null hypothesis with a less than or equal to. But for here, right, this sentence is for us actually sneakily giving us both the null hypothesis and the alternative hypothesis in one, right? So the manufacturer's claim should tell us the null hypothesis. So we take that number and set it for the null hypothesis. But if we are worried about the manufacturer's claims, that means we think they're incorrect, right? So that means that if we're trying to test and see whether their claims are incorrect, we want to know whether it's actually true that mu is bigger than 20. Right? So the claim was that it was less than 20. We want to see if there's enough evidence to suggest that it's more than 20. Right? So we set it up as our null hypothesis is that equal to 20. And our alternative hypothesis is opposite of the manufacturer's claim, right? So that's how, when we have this rule, since we have this rule about null hypothesis always being equal statements, that means that any claims, any status quos, any currently believed, any previously found information that's talking about not an equal to statement is secretly telling us that the alternative should be this opposite of whatever that not an equal to statement is. Right? So moving on from that, percentage fat in general here, we're assuming has a specific standard deviation. So that was not information about our sample. That was information given about the population, because this is just a statement about percentage fat content in general, right? It's not talking about in our sample specifically, right? And again, just gives us an alpha straight off. And so those are our hypotheses. That's all the data we can get from this word problem. So our test statistic, right, we're dealing with the mean, and we know what sigma is, so it's going to be a z, not a t. And our formula is x bar minus mu over sigma divided by the square root of n. Right, so that's going to be 21 minus 20 all over 4 divided by the square root of 30, which when I plug that into a calculator, we get 1.37. Right. And so let's say, suppose we fail to reject H naught, right? So this is our conclusion. If I can spell that correctly. So our interpretation is that there was not enough evidence to support the consumer groups worries that the average fat content was not less than or equal to 20%. So failing to reject never means that we showed anything. It means there wasn't enough evidence to go against the status quo. At least at that level of significance. Turns out there's plenty of room there, so let's scooch this back up. So we start off saying the cure rate for a standard treatment of disease is 45%. Now, here, when we look at this from this very first thing, right, standard tells us that this sentence is probably going to be about H naught. Right? And then if we look at what it's talking about cure rate. Right? So in other words, this is saying the proportion of the population that is cured by this treatment is 45%. Right? So this is looking at P equals 45%. Once we have that set up, that tells us that our alternative hypothesis is that P is something compared to 45%. Right? And if we go on to read the next sentence, Dr. Rogers had perfected a primitive treatment which he claims is much better. Right? So that sounds like he's claiming that rather than his cure rate being the same as the standard treatment, he's claiming that it's better. Right? And when we're talking about a cure rate, a better cure rate means a bigger proportion. Right? Better doesn't always mean bigger. Right? You can't look at a proportion problem and say every time you see the word better, it's going to mean a greater than sign. But in terms of a cure rate, I think we can all agree that a bigger proportion being cured is better. Right? So bringing up evidence, which is probably going to be a sample, because if we had a full population evidence, then there would be no need for statistics. Right, and here he specifies that he did the new treatment on 80 people. Right, so that tells us that n equals 80, and cured 40 of them. Right, so p hat is going to be the number cured over the total number, so that's going to be 50%. Right. So we have our two hypotheses set up here, right? And we mentioned that our test statistic for proportion is always going to be a z, and it's p hat minus p divided by the square root of p times 1 minus p over n. So this is 0.5 minus 0.45 all over the square root of 0.45, 0.55, all over 80. Right, and I plug that into my calculator, and I'm having difficulty reading my handwriting, but this is either 0.90 or 0.80, but I'm pretty sure it's 0.90. I think I recall that. Right? So that gets us our test statistic. Lastly, let's assume we reject H naught, right? So this is our conclusion, because it's always going to be one of these two options. Our interpretation, then if we're rejecting H naught, that means that we have enough evidence to support our alternative hypothesis. So with a 1% level, I guess I should have written down alpha over here, 1% level of significance, we are confident that the new treatment is better. Right? Because that's what it would mean for the cure rate to be bigger than 45%, is that it's better than the standard treatment there. Right? So, this is a lot of the hard work for the next two sections, right? We're going to learn how we can plug this Z in two different ways. At least if we know sigma. There's only one way if we don't know sigma. To actually reach these conclusions, right? Rather than me just handing it to us, we're going to figure out how to find it on our own. But that'll be for next time. So I'll see y'all later.